Section 50, conservative vector fields and independence of path. Suppose that you are told that f of xy is equal to x squared I xyj. And you're given two paths. And you want to show that the integral of f dot dr are the same. So you're given two paths. The first one, we'll call it A. We're told that r1 of t is ti plus t squared j. And the t goes from 0 to 1. Well then, dr1 is 1 to t, dt. Now, f of xy, remember this is x and this is y. So x is t. Square it, get t squared. So the j component is x times y. T times t squared, t cubed. So f is equal to t squared, t cubed. So therefore, f dot dr1 is multiply, get t squared, plus multiply, get 2t to the fourth. That's f dr. This is exactly what we want to integrate. We want to integrate f dot dr1. We want to integrate t squared plus 2t to the fourth as t fluctuates or goes between 0 and 1. Integral of t squared is t cubed over 3 plus 2t to the 5 over 5 from 0 to 1. 1 cubed over 3 plus 2 times 1 to the 5th is still 2 over 5. When you plug in 0, you get 0. And this happens to be 11/15. Okay, that's along path 1. What about path number 2, or part B? You're told that r2 of theta is sine theta I plus sine square theta j. And theta goes between 0 pi over 2. Okay? So dr2 would be cosine theta I plus 2 sine theta cosine theta j. All times, run out of room there, but all times dt. And f is still the same as above. It's t squared, t cubed. So f dot dr actually, that's absurd. Let's find out what f is. Now, we know from the beginning that f is x squared xy, where that's x and that's y. So x squared cosine square theta, comma, xy. Multiply these two. You get 2 sine theta cosine square theta. That is f. So now dot dr, integral of that, well, f dot dr, we multiply the x's, and you get cosine cubed theta, plus, now you multiply the y's, and you get 4, 2 times 2 is 4, sine theta times sine theta, sine square theta, cosine cubed theta. Cosine squared times cosine theta, cosine cubed theta. You want to integrate that, and of course this should be d theta, not dt. D theta. And theta goes from 0 to pi over 2. The first thing I would do is factor out a cosine theta. Actually, I wouldn't. If that 4 wasn't there, I would. Okay, remember, the first part gave us 11 over 15. I need the space on the left, and I want to make sure I get the same answer for this new part. This is showing independence of path. Yeah. Apparently I even have a mistake here. Sorry. Okay. X squared. I think I looked over here for x squared. X is sine theta. So x squared, sine square theta, times x times y. X times y is sine theta times sine square theta. It is sine cubed theta. Set that. So f dot dr, you multiply those two, you get sine square theta cosine theta, plus, now you multiply these two, you get 2 sine to the 4th theta cosine theta. And we want to integrate this, d theta. We want to integrate it. But integrating this is straightforward. Sine squared theta cosine theta plus 2 sine to the 4th theta cosine theta d theta. If I call sine theta u, this is u squared, and what's left over is du. It's just u to the 3 over 3 plus the 2. This integral, call sine theta u, du. That's u to the 5th over 5. U to the 5th over 5. From 0 to pi over 2. They told me those limits. The sine of pi over 2 is 1. Cube 1, get 1 over 3 plus 1 to the 5th is 1 times 2 over 5. And the sine of 0 is 0. So both of these pieces will be 0. So once again, we get 11/5. Exactly what we were supposed to get. So it turns out that the same two paths yield the same answer. Now you should make sure that the paths are going, they're starting at the same place and they're going to the same place. I think that's important. The first one told us that R1 of t was ti plus t squared j, and that t went between 0 and 1. Well, when t is 0, R1 of 0 is 0i plus 0 squared, which is 0j. That is, it starts at 0, 0. And R1 of 1, I'm letting t be 1 now, you get 1i plus 1 squared, which is 1j, 1, 1. That is, it goes from 0, 0 to 1, 1. Now, for the second path, we were told that R2 was sine theta I plus sine squared theta j, and that theta went between 0 and pi over 2. Now, R2 of 0, sine of 0 is 0, 0 squared is 0. It's just 0i plus 0j, which gives us the point 0, 0. Now, R2 of pi over 2. Sine of pi over 2 is 1. So you get sine of pi over 2 is 1i plus sine of pi over 2 is 1 squared. It's still 1j, which gives us 1, 1. So it's from 0, 0 to 1, 1, just like the first one did. Okay. I would definitely, now I wrote a lot, but you can do that real quickly in your head. Like 0, 0, 1, 1. 0, plugging in 0 is easy, plugging in 1 is easy. If on an exam, teacher says to show that it's path independent, and you do a real quick check and you realize that the paths are not even the same, you can say this problem makes no sense. The paths are different. And you get full credit and you do nothing. Except some very unnice classmate of yours is going to bring that to the teacher's attention, which I think you should never do. Because if you bring it to your instructor's attention, he or she is going to rewrite the problem, and now you have to do the work. Whereas a moment ago, you didn't have to do the work. Okay, so we want to find the value of the line integral f dot dr over some path C. And in our case, we're told that the path is t, and t goes between 0 and 1. Well, first we have to find f for t, because I need to write this using t's. X and y, they're both t's. Okay, so you get ti minus tj. X is t, and y is t. So now I have f for t. Now, dr is 1, 1, so 1i plus 1j dt. So the integral of f dr, well, f dr is, you multiply the I components, you multiply the j components, and you multiply it by the constant. So this is 0 dt to 0. And for the record, the limits are from 0 to 1. And that finishes up that problem. Suppose you wanted to integrate y squared dx plus 2xy dy, and the path is as follows. That, of course, is 0, 0. This point is 3, 4. And this point is 4, 4. Now, you can integrate over this path. You would make it two path. You would first go along here, and then you would go along here. But there are easier ways of doing this problem. We call this M and that N. The partial of M with respect to Y, regardless of what this is, it's with respect to Y. That's 2Y. And the partial of N with respect to always X, well, you have 2Y. 2xy, of course, is the same as 2y times x. 2y is a constant. With respect to x, 2y is a constant. With respect to x, the partial is 2y. Since both of these are equal, since both of them are equal, there's an easier way of doing this problem. We can try to figure out, now, this here, that's the vector field. That's big F of x. Actually, that's big F of x. Now, little f of x is just going to be, okay, let me say this correctly. YFF is y squared dx plus dxy dy. Like I said, f is x squared y plus 2xy j. So then so this here must be little fx, and this must be little fy. So if little fx is y squared, then f must be xy squared, plus possibly some function of y. A little bit sloppy with that earlier. Fy is 2xy. So f must be xy squared plus some function of x. So now I need for these to be equal. And that's just by saying that f is x squared y. So this top integral is equal to x squared y from the beginning point 0, 0 to the final point 4, 4. So when you substitute, first you do the upper limit. You let x and y both be 4. That's called the coincident. 4 squared times 4 minus, then you let x and y be 0. 0 squared times 0. This is 4 cubed, or 64. So you don't have to go along the path. You don't have to find the equation of that line, so you can find R1 of t. Plus, then you have to find another path. You don't have to do that. You can just show that it's conservative. You show that you show this right here, that dm dy equals dn dx. That eats 3 sets of problems. If they're equal, it's independent of path. Those two are equal. Doesn't matter what path you use. Suppose you have 2x minus 3y plus 1 dx minus 3x plus y minus 5 dy. This is m, including the negative sign, that's n. So the partial of m with respect to x, this is a constant, the derivative is 0. The partial of that, I think I said it right, but I wrote it wrong. The partial of m with respect to y. That's a constant, so its partial is 0. This is a function of y. The partial is negative 3. Okay. Now I want to find the partial of n with respect to x. Only this is a function of x. This has a constant. The derivative is 0. The derivative of negative 3x is negative 3. These two are equal. Okay, so then we say, all right, fx equals this. 2x minus 3y plus a constant. And fy equals this. I'm going to distribute the negative sign. Equals that. So what could f be? Well, that would have to be x squared. So then fx will give you 2x minus. For fx to give you a constant like 3y, you must have started off with 3i times x, or 3xy. Plus, for the partial, for the derivative with respect to x to be 1, you had to start off with x, plus some function of y. Because if you add a function of y, when you take the partial with x, this is 2x minus 3y plus 1 plus 0. Plus if it's in terms of y, then the partial will be 0 with respect to x. Okay. Now we're using this rule. If the partial with respect to y just gave you a constant, then it must have been that constant times y. Minus. For the partial to be y, you must have started off with y squared over 2. Plus 5y. So now, combining these, we know that f of xy is x squared minus 3xy plus x. Well, I already wrote down this. I didn't write down this. And it won't affect the fx because it won't affect it. It's still going to come back to this. Because the partial of y squared over 2 with respect to x is 0. Same argument for adding on 5y. Now you may say, but over here, we added on x squared and x. Doesn't matter. With respect to y, those partials are 0. So that's f. That is what we want to integrate. I forgot to give you the path, excuse me. So this is going to equal to, this top line is going to equal to this minus y squared over 2 plus 5y. And, okay, so good. I could erase 90% of this. So let me do a couple of parts. If one path was this, y equal e to the x, and it goes from 0, 1 to 2e squared. Well, then that's what you would do. You would go from 0, 1 to 2e squared. So when you plug in 2e squared, remember that's x and that's y. So reading this down, you get x squared minus 3 times x times y plus x minus y squared over 2 plus 5y plus 5y minus, now you plug in the lower limit, minus x squared minus 3 times x times y, x is 0, y is 1, plus x minus y squared over 2 plus 5 times 1. This is arithmetic. Work it out. And you'll get an answer. You'll get an answer. Now, here's an easier one. Once you realize it's conservative, that is, once you realize that dm dy equals partial n with respect to x, once you realize that those two are equal, okay, once you realize that these two are equal, you want to hope for the following. You want to hope that you are given a closed region, a closed path. You want to hope you're given a closed path. Let me just call this a for a moment so I don't have to keep writing the whole entire integral. Let me write the whole entire integral anyways. This integral, since it's conservative, since it is conservative, this integral, since it's conservative, that is, this is true, and it is a closed path, tends to 0. So you didn't have to do anything else once you realize that these two are equal and it's a closed path. So if you were given this path, if you were given this path from -1 to 1, for example, you would say the integral is 0. Once you realize this was true. If it's conservative and you have a closed path, then the integral is always 0. It's really good to know that because you don't want to do the integration. I'd rather just look at a problem and say, oh, that's 0, rather than working it out and then showing that it's 0. If somebody asks me, what is the derivative with respect to x, so sine squared x plus cosine squared x, I want to recognize this as 1 and say, oh, this is the same as the derivative of 1, which is 0. Rather than saying the derivative of this is 2 sine x cosine x plus 2 cosine x times the derivative of cosine x, which is minus sine x, and say, oh, this and this are the same, I'm subtracting 0. Okay, I'd rather just jump right to it, whether I can immediately say it's 0 or 17. If it's conservative and you're integrating around the closed region, the answer is 0. Okay, 1, 2, 3, done. It's 0. Okay, suppose you're told that f of x, y, z is yz, xz, and xy. told that the path is ti 2j plus tk, and t fluctuates between 0 and 4. Now, if you were to compute the curl of f, partial with respect to x, with respect to y, with respect to z, repeat the first two columns. You have yz, xz, xy. Repeat the first two columns. I, j, k, I, j. Well, this product, the partial of this with respect to y is x times I. It's xi. This product, with respect to z, the partial is y times j. With respect to x, it's z in the k direction, minus, in this direction, the partial of this with respect to y is z times k, zk. Plus zk plus zk, we're subtracting bye-bye. With respect to z, that's x, xi, plus xi, plus xi, plus xi, subtract, goodbye xi. And the last one, with respect to x, this is y in the j direction, plus y, j. It's 0. Since the curl is 0, that means we are conservative. Okay, that means we are conservative. Okay. That's the same as, well, we did partial n with respect to y equals partial n with respect to x. This one we have just x and y. So now we have z's, so we find the curl. Now the curl is 0. Now, what would be nice is to know if this is going back to the same place. When t is 0, we get t is 0, 2, 0. And r of 4 is 4, 2, 4. T is 4, 4. T is 4, 4. The second component is always 2. So we're going between those 2 points. Now, what we need to do is find a potential function for f of x, y, z. Now remember, this is fx. So f must be x, y, z. And if that's fy, then f must be fy, z. Because remember, that's the constant. What did you take the derivative of with respect to y to get xz, xzy? Same thing here. If that's xz, f must have been xyz. So there is our potential function. So we're done. The problem asks us to find f dot dr. Well, this should be, I guess, a little f. Little f. So it must be the potential from the start to the finish. From 0 to 0, that was the start to the finish. 4, 2, 4. So you multiply x, y, and z. It tells me 4 times 2 is 8, times 4 is 32, minus 0 times 2 is 0, times 0 is 0, the answer is 32. It was a lot easier than integrating along the path. In fact, This is in R3. It's not so easy to even know what that path looks like. It turned out it's kind of two-dimension because the y value is always 2. This is the graph x equals 2. This is the graph that, x is equal to z, because the x and the z value are the same, but y is always 2. Pictures a line. Here's the x-axis, and here's the z-axis. Here's y equals z, or x equals z. Now the y value comes right out of the board. Imagine this line coming straight out of the board, and also into the board. Well, something's wrong with that comment. Imagine this line comes out of the board 2 units. That would make y equal 2. It just comes out of the board 2 units. Sorry about that. Just comes out of the board 2 units. But nonetheless, the integral is 32. Since it was independent of path, we just took the path right from the start to the finish as a straight line. I guess that's why they call it line integrals. Okay, let us try this one. Evaluate the given line integral using the fundamental theorem of line integrals. Well, if you have the integral from yi xj dot dr, and it's a smooth curve from 0, 0 to 3/8. Since it's a smooth curve, we can play the game we've been doing. Let's see if it's conservative. The partial of y, the partial with respect to y, of y is 1. But you know what? That's the same as the partial of n with respect to x. This is partial m dy. This is partial n dx. N is just x. M is just y in this case. But nonetheless, they're equal. This and this are equal. They both equal 1. That means it is conservative. Okay? So, this here is fx, and this here is fy. So fx equals y, and fy is equal to x. We're taking the partial with respect to x, and we get y, a constant. That means we must have started off with xy. Same for the bottom. We started off with xy. So a potential is f equals xy. So this top integral is nothing more than xy evaluated from 0, 0 to 3/8. This is to multiply x and y. Okay, x times y is 24 minus x times y is 0. The answer is a quick 24. You don't have to integrate. You don't have to integrate around the path. And you should read your book and learn what type of path this works for. Any path, a smooth path, what type of a path does this work for? Now, what if you have this problem? One more. Integral of z plus 2y dx plus 2x minus z dy plus x minus z dz. Now, if you call f this I plus this j plus that z, z plus 2yi plus 2x minus zj plus x minus zk. You can figure out that the curl is 0. You can do that calculation and you can get that the curl is 0. That implies conservative. That implies path independent. Doesn't matter what the path is. Okay, it doesn't matter what the path is. Now I'll bother to tell you what the path is. Suppose it's from this point to that point. Suppose that's the path. Well, first we need to find the potential function. Remember, this is fx, this is fy, and this is fz. If fx is z plus 2y, which is a constant in terms of x, so f must be that times x. F must be zx plus 2yx. And if fy is 2x minus z, there's no y's in there. So multiply by y. Fz is f minus z. So f must be xz minus z squared over 2. So now, let us see what we need. We have to have zx, which 2 of them needed. We have to have 2xy, which 2 of them needed. We have to have zy. Now that shouldn't have x's in it, else it would mess up this, but it doesn't. And you have to have minus z squared over 2. This is our potential. So the answer is zx plus 2xy minus zy minus z squared over 2 from 0, 0, 0 to 1, 1, 1. X, y, and z are 1. So z times x, 1 times 1 is 1, plus 2 times 1 times 1, minus 1 times 1, minus a half. When you plug in zeros for all the variables, you'll get 0, of course. 1 minus 1 is 0. So left with 2 minus a half, which is 1 and a half. And that's the value of the integral. It's 3 over 2. Okay, that finishes this section. Good luck with it.